right, good afternoon, everybody. So today I want to spend some time going over some Excel work. Glad to see some of you have your laptops ready. I wanted to just touch on for like 2 minutes a couple of related concepts that we didn't really get into. I'm not going to test you on this with this exam, the coming one, because we didn't really talk about it or have homeworks on it. But it's certainly related, and I probably should have covered it to an extent. So I wanted to kind of make you aware of those. So that's today. I want to go through those things. Then Thursday, the homework will be due, and we'll have an exam review. Exam will be a week from today, of course, and then we'll get on to kind of our last section. Wanted to make a note. Had some things come up in the department. In 2 weeks, I'm going to be taking on a third class, which means I'll be lecturing 3 times on Tuesdays, Thursdays, starting in a couple weeks for the remainder of the semester. So if I'm talking like this, you'll know why. I expect I might have some trouble, right? I don't love talking in general, so 3 hour-and-a-half sessions per day is going to be a lot. So maybe I'll have some more guest lectures to help fill in or whatever. Just please be patient with me. This will be the last lecture of the day, which is why I'm warning you coming up. I don't think it should impact you. I'll do my very best to make sure it doesn't impact you in terms of learning. So just bear with me. Next couple weeks, though, should be just like normal. Okay, so today just wanted to touch on these 2 concepts called hardness and alkalinity. So hardness is, we mentioned it before, we probably showed you this little graph of how hard is the water, especially groundwater in different places. Really, it's a measure of mineral content. So typically we talk about that in terms of calcium 2+ and magnesium 2+. Now, the way we report it, if we're going to talk about hardness, is using either milliequivalents per liter, and that's kind of like equivalence of charge provided by the minerals. You can think of it that way. So milliequivalents per liter is sort of like millimolar per liter, but millimolar of charge with some basis. So there's some unit conversions. Maybe we'll touch on this after the exam and do some practice with it. So you can describe it that way, or as what we would call milligrams per liter as CO3. So how much hardness is there as if it was all in the form of calcium carbonate? So it's a typical convention. There's a couple of reasons why it's convenient. It really is just a unit conversion deal, and it's a way to deal with the molar conversions, mass to molar, on the front end instead of the back end of a problem. And so then you can talk about all of these, the hardness and the alkalinity, in terms of some sort of mass concentration, because you've already made that adjustment. So hardness is mineral related. Alkalinity is essentially the acid buffering capacity of water. So when you add vinegar and baking soda, you get some reaction, right? So that's what the little video here is about. It's supposed to be a GIF. So anyway, you add that and it's reacting. And essentially what you've got there is vinegar, which is an acid, which is essentially adding H+. And then you've got baking soda, which is typically sodium bicarbonate. So probably Na2CO3. And so that's essentially adding lots of carbonate, CO3 2-, which when you put them together, acid and carbonate, it's reacting and you're forming lots of CO2 bubbles. So that's what we're getting out of this. In fact, fun little demonstration, I probably should have come with this today because that would have been fun, is you can actually douse a candle. So you can extinguish a candle if you have a candle flame going, and you take some vinegar and baking soda, mix it together in a little jar, a cup or something, and then you've got a lot of CO2 gas right there. It's kind of pushed all the other air away. And then you pour that onto the candle without pouring the liquid. You're just pouring the gas, and it's slightly more dense than air. And so it'll sort of pour onto the candle flame and extinguish it. Kind of fun little fun little experiment you can try at home. And so essentially what you're doing here, and why I'm relating this to this alkalinity concept, is how much acid can you handle before the pH is changing too much. So you've got this type of reaction happening when you add some acid, and if it's just going through this reaction and cause, the H plus is adding to make it HCO3 minus, and you continue adding, so you get H2CO3. You see how we're adding those protons there, and then eventually, once you're in this form, that's in equilibrium with CO2 gas and water, right? You just add a water to CO2 gas, you get H2CO3. So that system and similar buffering systems is what we call alkalinity. How much can a solution take? So you'll deal with that more in some other classes, I'm sure, as you go. I wanted to talk about it briefly because it is kind of relevant to our equilibrium reactions. Lots of things going on, especially with these particular reactions. But like I said, we're not going to directly deal with the mechanics of all this. So, again, not dealing with this, not going to put this on your exam, because I haven't given you any homeworks on it, but this equivalent I was talking about, the milli equivalence, really is looking at that equivalence of charge, and here's a few details of how it's calculated. It's essentially the atomic weight or molecular weight of something, so an equivalent weight is, and divide that by the ionic charge, or basically the number of protons that the material can absorb, or can that are required to replace that cation. So to replace calcium, you need 2 protons, right? So for CaCO3, you have 2 because the calcium there is a 2+, even though there's no charge in CaCO3 in total. In order to replace that calcium, you need 2 protons. So that's kind of what the deal is. And the molecular weight for CaCO3 happens to be exactly 100. So it's kind of a convenient reference point. So that's why we use as CaCO3 in so many problems. It's just a handy round 100, because if you look at calcium's about 40, carbon is 12, and then you have 3 oxygens, it all adds up to 100. So divide that by 2, you get 50, and that's 50 grams of CaCO3 per equivalent charge that it satisfies. So that's kind of what it's talking about, and then you can use that equivalent weight to calculate a milli equivalents per liter. It's just basically doing the conversion from milligrams to this charge equivalent thing. Instead of milligrams to moles or to millimoles, it's doing that. So we might come back to that. I just wanted to make you aware there's a little bit of unit conversion for these particular topics that are relevant to equilibrium chemistry. We will certainly revisit this in the future in our program. Okay, so last time we left off taking a look at the ammonia problem, and today I kind of want to get into slightly more complicated systems using more than just a single proton reaction, so the NH3 NH4 plus system, but similar principles here in terms of, okay, how are we going to graph this, maybe pH versus the fraction. So we've got this alpha fraction here, and specifically relating to the homework that I assigned. So if you took a look yet, would hope that you've taken a look. The activity essentially I gave you was, I found it from somebody else's course. I thought it was pretty useful and a good way to give you stepwise instructions for an Excel problem. One of you have already mentioned to me, oh, there's maybe some confusion about how things are worded, but it's partly why I wanted to talk you through it a little bit today and give a similar example. So I thought this would be good practice. It's directly relevant to the course material and some hands-on Excel work. So this was the system, and I asked you to answer a couple of these questions, I think 1, 2, and 4, something like that. And then as I was looking over it and discussing with one of you, I noticed that it was talking about these alpha fractions, which didn't really specify what those were. And so as I was kind of taking a look to see exactly how to phrase that, we had actually talked about it in a sense, but I hadn't phrased it that way. I came across that same professor had another resource, related activity. It's kind of the first Google hit in looking at these alpha fractions on this topic. So I figured that might be a good place for you guys to look. This is now posted to Moodle, and it talks through kind of this alpha fraction for a single proton system, and we'll work through that today and expand that to a diprotic acid. So just protic, protons, 2 protons instead of just 1, like the ammonia case. Okay, so there's a few resources here on this slide. This last one is what I was just showing you. These other 2 I didn't end up making too much use of. I just found some Excel practice. I mentioned it last time. I didn't go that route, but certainly take a look if you're interested. Might be useful, might be, if you're looking for more homework, feel free to assign yourself some. Okay, so the alpha fractions method. I want to try to elaborate on what that problem is talking about and what that approach is a little bit more clearly. Hopefully I can show you where we've done this before, and then hopefully that will make some sense. So the alpha fraction is really specifically talking about the fractional amount of something, of an acid, that exists in a certain form. So I think we had talked about the chlorine example. HOCl is in equilibrium with H plus and OCl minus. And so what fraction of the chlorine is in the hypochlorous acid form, for example, is a big question. That's an important question for disinfection because that's the more effective one. So if we're talking about the alpha HOCl, what we're talking about is the amount that's in HOCl form compared to the total, which would be HOCl plus OCl minus. So I think we've seen that before as, okay, what is the fraction of, the fraction that is whatever. Writing it as this alpha might be slightly new, but you probably now recognize that it's in a few places in the problems, examples, or something, even though I didn't teach it that way. We also, when dealing with this, we talked about swapping and simplifying to get this whole equation in a form that's not just a whole bunch of unknowns, right? If we don't know HOCl and we don't know OCl minus, then that's 2 unknowns and that's not very good. And so this worksheet, this alpha fractions worksheet, brings us essentially to that point and then asks us to simplify it. And I want to kind of show you what they're doing here and what the symbols are meaning. So here they say the alpha of A minus. So that's the, I guess you'd call it the conjugate base for this acid, meaning if we've got hypochlorous acid, if that's A, then A minus, I guess that would be A with a hydrogen on it. So the hydrogen and the acid, that's HA. And then over here, the OCl minus is just that conjugate base, meaning that it's lost the hydrogen, it's lost the proton. So that's what we're talking about when we're dealing with these HAs and these A minuses. So just talking about an A and an H is a generic form, because that you can apply that to any acid, right? So that if A is an acid, then any acid could work that way. You could even do H2O and in equilibrium with H plus and OH minus, and in that case, OH is the A and H2O is the HA, right? You can swap that with anything that is an equilibrium protonation reaction, or whatever the proper chemical way of saying that is. Okay, so with that, well, what we want to do in many cases is get this, instead of in terms of HOCl and OCl minus, we'd like to have it in terms of the pH, because that's easily measured and manipulated, and the equilibrium constant. So that hopefully triggers a thought of what we've done before, where we can say, we know that for a given equilibrium constant, that's, at least in this form, that's going to be, so in this case, I'll just write it for this example, and then we'll see how that's written out in the general form. So this is going to be H plus times OCl minus divided by the HOCl. Okay? And we can get that we can simplify this to get the ratio between OCl minus and HOCl in the form of the Ka and the H plus. So I'll just divide both sides by H plus, and then we get OCl minus divided by HOCl equals Ka divided by H plus. Right? So that's something that we've, this is a process we've done before. And then if we divide, so that's one equation. And I'm going to just kind of set that aside here. So that's one. And now if we come back to our other one and simplify this one a little bit, we can divide the numerator and the denominator by HOCl. That'll give us 1 divided by 1 plus OCl minus divided by HOCl. Then we substitute, since that's exactly what we have over here in this other equation that was related to our equilibrium, we can sub that straight into there, and now we have this alpha fraction in a form of just the equilibrium constant and the amount of protons, the H plus. So that's essentially where this worksheet is headed, is to understand it in that format. It also introduces a different concept. You see, okay, so that's one part of it, and I think the worksheet will get there. Let me come back to showing you what specifically the worksheet is dealing with here. So we have two different fractions, the fraction for A minus or the fraction for A. So in our example here, that would be the fraction of OCl minus and the fraction of HOCl. And what they're doing here with the CA, well, first of all, the fraction that is OCl minus, that's going to be OCl minus divided by the sum of the two. That's exactly what we wrote here. So this is just kind of looking back at where we were a moment ago. So instead of HOCl, you just put OCl minus there, and that's the fraction for OCl minus. So that's just the generic form there that they're describing. We can also write the total, and this is what the worksheet does, as Ca. So they say the analytical concentration, that's the total amount of acid there. So that's the HOCl plus the OCl minus. So that's their terminology there. And then when we break it down into the brackets here for HA, that's the actual concentration of the stuff that has not been dissociated, and A minus is that portion that is dissociated. Okay, so moving from there, and I'm sorry, I probably should have kept this on this part on that previous page. When we move it forward, and I'll go back to the PDF in a moment, we can get this fraction here, if we wanted to, into this form. So the Ka divided by the Ka plus, here it says H3O plus. That's just meaning protons. I don't know why they do that, but they just mean H plus. It's the same thing. It's a water plus that is the same thing as just writing the hydrogen. And they also note that the total fraction, again, this is for the monoprotic system, meaning there's one hydrogen that can be added or subtracted. The total of the two fractions is 1, right? So 50% plus 50% is 100%, or 0.5 plus 0.5, whatever the case may be. So that's kind of a simple fraction analysis there. Okay, and we could get to this particular form of it by doing this process with OCl minus here, and then rearranging accordingly. Okay, so I want to come back to this PDF then. So it's talking about these alpha fractions, it's introducing the concept, and it says, okay, look how we did it for these monoprotic weak acids. We define that fraction as a fraction of total, if Ca is the total. And then it's asking us, as to step you through the process that we just went through. It's saying, okay, write a reaction for the dissociation of the generic acid and water. So that's what we did with HOCl is in equilibrium with OCl minus and H plus. So that's that step. Then it says write an expression for the dissociation constant Ka for that acid in terms of the molar concentration. So that was the next step we did. So if we were to track with that PDF there, then essentially this was step one, write out that, step one. Step two is write an expression for Ka, that's 2 here. Then we continue on, it says solve for A minus in terms of HA, H plus, and Ka. I ended up solving for A minus divided by A, right, HA, excuse me. So they wanted us to just take A minus there. So that would have just been solving this for OCl minus. So 3 would have been solve for that. So this is sort of like part 3. And then it said using that, solve for the alpha fraction in terms of HA, H plus, and Ka only. So in that case, they were leaving the HA in the system. It's the same process, just manipulating the algebra here. So that's kind of like 3, and then this part would be pretty much 4, step 4 there. And then in this case, it says eliminate HA and solve. So that's where we essentially eliminated HA when we divided by the top and the bottom by HA. So this step here was kind of 5. We just did it in slightly different order. Because you can do that substitution before or after. It doesn't matter too much. Okay, and then it says if you've done this correctly, you should be able to simplify for the following. Now, keep in mind, I ended up solving for HA, the fraction for HA. They solved for the fraction of A minus. So that's why ours looks a little bit different. So ours, by the way, so what we solved for was HA equals 1 over 1 plus, this was Ka over H plus. Now, if you had solved instead for OCl minus, you would have landed at their expression right here with a Ka divided by Ka plus H plus. And if you divided the top and the bottom there by Ka, you'd have 1 over 1 plus H plus over Ka, right? Which is exactly the inverse of what we have here. So that's how the fractions, they sort of are opposite of each other in that manner. Okay, then if you wanted to solve, if you had that version and wanted to solve for the other, the easy way to do that would just be to do 1 minus that fraction, and that'll give you the other one. Okay, so then it goes on and gives another thing to do, kind of related. I'm going to skip over that. Okay, so then it gives, so it goes on just a little bit. Might be worth working through that as you go if you wanted to master that in the terms that he's giving. But if you followed this process of combining those two equations, you should be able to apply some algebra to that to get to some other answer that you might need, right? And specifically what's going on here is we're calling that the alpha fraction method, okay? That's kind of the difference. We've already seen it, but he's elaborating on it in that manner. Okay, so what I would like to do now is, and it goes on with some graphing. So most of the next parts of this are graphing, which is kind of what the Excel assignment is doing in the first place, except it's doing it on a polyproduct system. And so they give then some discussion here, and what I'd like to do is to see if we can essentially analyze a separate system, which maybe I chose a poorly chose one. I was thinking to myself, well, sulfuric acid is diproduct, maybe that'll be a good example. But as I'm thinking about it now, this is technically a strong acid and not a weak acid, so it might not work out as well, but we'll explain that in a minute. Mostly what I want to do is make sure that we can get to these alpha fractions that they're referring to and simplify them into these guys. So in this pamphlet they have, or this PDF they have, these three fractions that we're going to take a look at, and then it says derive, and then you have these three, right? So I want to see if we can expound on that, derive this. Yeah.
You were saying the equivalent weights won't be on the test Tuesday, but this will?
Yeah, so that's correct. So the equivalent weights, not putting on the exam, but this method we have gone over, and so I'm trying to make it more clear and elaborate on it. It's also in your homework. So I'm hoping that with all of this, I will be having equilibrium problems on the exam, and so I'm hoping that this stuff today is just filling in a little bit more thoroughly and making sure that you're understanding what the homework is asking for, and can solve it that way. So if this is not helpful, feel free to stop me and ask me other questions about Excel or whatever. Totally flexible, because this is basically the extent of the slides I have, and I was planning to do some more Excel stuff, kind of plot out what it would look like for a different system and kind of work through it with you a bit. So if you have other needs or desires, let me know. Okay, so then it says the results. So we have the prompt here and kind of our basic fractions, or our initial fractions. Talk about that in a moment. And then it says if you derive them correctly, they should look like this. So I suppose a good thing to practice here, or to take a look at. So let's come back to here. What they're saying with this alpha of A2 minus, this is the fraction, and let's take for a moment sulfuric acid. Even if it's a bad example, we'll pretend like it's a good one, and it'll make enough sense. So sulfuric acid, let's say, is going to be in equilibrium first with H1 SO4 minus plus H plus. And specifically, I think that reaction, the pKa is negative, which means it's kind of never going to happen. It's always going to dissociate. So that's why the example is perhaps too silly. However, let's pretend that makes sense, and we'll move on to that guy being in equilibrium with sulfate, SO4 2 minus, and H plus. So if that's our system, imagining that it's realistic, that's our diproduct system. That's what we're talking about with this alpha with a 2 minus. So that would be A2 minus is right here. This guy would be A1 minus. And this guy is our HA, our protonated acid. Okay, so that's kind of what we're talking about. So if I were to rewrite this alpha, what I would say is alpha for SO4 2 minus is equal to concentration of SO4 2 minus divided by the total amount of acid in the system, right? We could write it as Ca, the analytical concentration. We know we added 50 milligrams per liter of this or whatever, or we can write it as, and of course we'd have to convert that to moles, or we could simply write it as the H2SO4 plus the HSO4 minus plus our SO4 2 minus. Okay, so that's hopefully that's makes sense, right? That's just kind of the direct way of phrasing the H2A here, the HA minus, A2 minus. Again, using A as a, and I guess we'll say that's HA minus, sorry. So this would be H2A. Okay, so that should then match the nomenclature. I apologize. Okay, with that, we can just describe the whole system that way. And so what we want to do is take this fraction and really do this for each of them and simplify so that, use this kind of same sort of method to simplify based on the equilibrium constants at play, simplify in the form of H plus and the KAs, which would be a KA1 and a KA2, let's say. This would be KA1. I think they just say K1 and K2, so I'll just do that. So K1 and K2. We want this fraction in those forms so that we can basically know everything about the system just with that. So that's the target. And if we're going to go ahead and work on this guy, our endpoint is supposed to look like this one. And I don't know why they reversed them, but they essentially reversed their order here. So we are starting with that one on the top, and we want that one on the bottom. That's what we know that we're supposed to derive to that form, because here it's the alpha of A2 minus. Down here, that's still the alpha of A2 minus. It's just has been solved in the form of the H plus and the K1 and K2. So let's see if we can do that. Specifically, I guess what I like to do is divide and see what happens if we get rid of the SO4 2 minus. This might not go so well, and maybe we ought to follow their specific instructions for the algebra, but I think it should work either way. So I'm going to go ahead and start by saying the alpha SO4 2 minus is equal to 1 divided by H2 SO4 over SO4 2 minus plus the HSO4 minus that divided by our SO4 2 minus plus 1. So that's one version of our fraction. And now what I'm thinking in my mind now is, I bet that if we take the two equilibrium equations, one of them, this guy should be able to swap into there once we write it out and get it in those terms. The other one might be a little trickier because we have this we have it divided by SO4 2 minus. So we're probably going to have to substitute something, maybe from this guy. We'll have to substitute something else for that. So that part might be a little trickier. I think it should just be another substitution. We'll just have to think about it when we get there. Okay, so let's write out the KA or the K1. Actually, let's start with K2 because that's looks like that'll be a direct substitution. So K2 is equal to the SO4 2 minus times H plus divided by HSO4 minus. And then we can rearrange that to get it in form of HSO4 2 minus, or excuse me, minus divided by SO4 2 minus. So we'll multiply both sides by that, divide both sides by SO4 2 minus, and then divide both sides by K2. So just swapping some stuff around, HSO4 minus divided by SO4 2 minus equals H plus divided by K2. Okay, so we can put that then in that spot. And that's going to need some more space. So we'll see if we can copy that over. You know what? I'm going to do this the easy way. Well, I say it's easy, but we'll see. No, that's not going to be. I'll just switch back and forth. Okay. So we had alpha of, this was SO4 2 minus, right? Yeah. That was equal to 1 over our, oops, sorry, didn't need to do that. Okay, so 1 over the H2SO4 just keep consistent color. That guy divided by the SO4 2 minus, plus that substitution that we were going to make, which is H plus over K2 plus 1. So we just need to simplify now. If we can get something in terms of the SO4 2 minus. So we do have, we could solve this part. We could get SO4 2 minus in terms of these two and HSO4 minus. So that's probably the best way to go. So what I'm going to do is I'm going to take essentially that same equation with K2 and solve it so that we can substitute, so we can have, instead of SO4 2 minus, we can have some form of HSO4 minus in order to do the other substitution here. So that we get a HSO4 minus here with some other stuff. Then we can use the same fraction swapping that we just did. The same type of method. Okay, so I think that'll make sense when I write it out here. So let's take the K2 one more time. So K2 is equal to SO4 2 minus times H plus over HSO4 minus. And we're going to solve this in terms of just the SO4. So SO4 2 minus is equal to K2 times HSO4 minus divided by H plus. Okay, does that make sense? Just took the same equilibrium reaction and solved it for something else. Now, if we plug this portion in right here, then that fraction should become something that we can relate to the K1 reaction. So let's try this. So alpha SO4 2 minus is equal to 1 over, that's a V. Let's try 1. 1 over, we've got H2SO4 divided by this stuff. So this is going to be, I'm just going to go ahead and put this H plus on top to keep it a little more clean, because that will come up on top here, dividing by that fraction. And what will be left down here is K2 and HSO4 minus. Then we have plus the H plus over K2 and plus 1. Okay, does that make sense? Sort of, maybe. Okay. From there, let's take our first equilibrium reaction, the K1, which we know to be our HSO4 minus times H plus divided by H2SO4. And I don't think it matters which portion you started on. I think you're just going to have to do that double substitution thing on one side or the other. Because I think you could have started with K1 and did this reaction. Let's see. No, I guess maybe not. I guess it depends on which fraction you're aiming at. Because if we aimed at a different fraction, then these denominators would be different, and then we'd have different substitutions to make. But it's the same process. So you make the substitutions as necessary. Okay, anyhow, we got this K1, we have this equation, and what I want is to be able to substitute it for this H2SO4 divided by HSO4. So what I'm going to do is multiply both sides by H2SO4, divide both sides by HSO4 minus, and divide both sides by K1. That gives us H plus over K1. Okay, so that's then a term that we can substitute in here. Of course, there's still going to be the added stuff involved, but this should give us finally our answer. So alpha for SO4 2 minus then would be equal to 1 over, we have H plus times H plus, so this H plus times this H plus, that's going to be H plus squared, divided by K1 times K2 and yeah, that was a substitution here for those two. Okay, so then we've got H plus squared divided by K1 times K2. Then we've got H plus over K2 plus 1. And once we get it to that point, it kind of looks like there's a bit of a pattern emerging. And now we can check to see if this is correct according to the solution that was provided. And they solved for the alpha of A2 minus, and looks like they took the K1 and the K2 on top. So they multiplied the top and the bottom by K1 and K2 compared to what we did. So I guess we'll do that real quick. So alpha SO4 2 minus equals, if we multiply the top and the bottom by K1 and K2, then we'll get K1, K2, and chances are they took a different algebraic route, which is why they have it like that. But let's just see what it looks like. Down here, this will just be H plus squared plus, this will be H plus times K1, because the K2s will cancel, plus K1 times K2. Okay, and that does turn out to be their answer, so that's good. They're also using the H3O plus. I just used H plus, keep it simple. Okay, so that was actually quite involved just to get one of these diprotic fractions. And so hopefully that's going to be helpful when you tackle this homework assignment. Essentially, that's the generic forms of them. So you can swap that in for any of them. And technically, now that you have this resource, you could just look at this and do it, right? But I would encourage you to work through the process on your own to make sure that you're comfortable doing these substitutions, because chances are you're going to use the alpha fractions in one way or another. We've already seen them in some sense where you had to swap. Hopefully this, the combination of these two worksheets, I'm hoping will kind of help make that a little bit more clear and comfortable for you. Okay, so if we take a look at that assignment then, and bring up Excel, wanted to take a quick look at what this might start looking like if we did it for sulfuric acid. So as I mentioned earlier, sulfuric acid is probably not a good one, because I do believe it's a strong acid, and I think the equilibrium reactions are really designed to handle weak acids, where it's actually legitimate to have both forms. A strong acid will completely dissociate and stay that way. So in reality, our H2SO4 is going to completely dissociate into these two, and then I think there is a bit of a weak acid here with HSO4 minus. And the reason I'm saying I think is because I haven't really looked into it. It's been a while since I've looked at the technical definitions, and I'm guessing based on the fact that I guess I can draw here too, that's good. Except that I can't erase it. The pK for the first reaction is negative 2.8. So I think unless we have basically all acid as our liquid, that's never going to happen. So we're never really going to have H2SO4 as a form. So if we do this process and graph it, hopefully we'll see that, yeah, we'll never actually see that H2SO4 because it's all already deprotonated at least the first time. That second one, the pKa is at 2. So if you get below pH 2, then maybe you have a little bit of the HSO4 minus in solution. It's not going to be very common. So at most pHs, if you're adding sulfuric acid, then you're just going to end up with protons and sulfate. So by the way, if you do ever work with sulfuric acid in particular, these reactions are very exothermic. You always want to add acid to water. Because it's more dense, and what you don't want to have happen is having a layer of acid underneath and water coming on top, and the water just sits on top, and this exothermic reaction right at the interface is happening and heating up. It will boil and explode from the pressure. And what I mean by explode is it just sprays water and acid everywhere. Don't want to do that, right? So if you're ever working with concentrated acids, make sure to look it up if you don't remember, but it's adding acid to water, assuming the acid is more dense. So sulfuric is one of those cases. Anyhow, so if we go into Excel and we take a look at the instructions that were given, one potential confusion here is that it's talking about naming some of the first cells, and then it goes on and says, okay, well, now that you've done that, insert these things into A1, B1, A2, B2, C, and D. And if you had put all of these names, which I started here, you named all these columns and you started in A, you just have to shift them over or maybe down. I just decided to start shifting them over, and then I decided, well, I'll label my work a little bit here and write a couple things there. So I just shifted everything down a bit. But essentially, it goes and says, okay, well, get your pKs from a table and then convert those to the K value. So that's going to be 10 to the negative pKa. So, and you see here that Ka value is very strange when we're normally looking at Ka values of like 10 to the minus 5th, 10 to the minus 7th, something like that. 630 as a Ka value is quite strange. Even the Ka2 here, 0.01, is quite high. Okay, so anyhow, it goes on, and I don't really want to do exactly the whole homework for you, and I don't think that would be a great use of my time, but I'll take through a few steps just how I would approach it. I haven't solved this thing myself yet. I was going to work on that tomorrow. So this was my initial approach here, and again, this is for the sulfuric case, but it's going to be very similar. And so first of all, the H plus, this should be pretty simple. H plus is going to be, so pH is 10 to the minus of x, right? So the H plus is 10 to the minus pH. So at pH 0, you have 1 mole per liter of protons. Should be able to fill this downward. And it should fill nicely like that. The OH minus is essentially going to be inverse of that. So there's probably a simple way to do this. I'm trying to think. I mean, the long way would just be to do exactly that. You know what we could do is we could do 10 to the minus and then do 14 minus the pH, because that'll kind of invert it for us. So then that should give us kind of the opposite trend, which should match up. If we wanted to double check ourselves here that what I did was correct, we should be able to multiply the two with each other and always get 10 to the minus 14th, because that's the definition of the KW, right? So I'm just going to do that. It all checks out, so I'm happy with that. Okay. So you could do this a little bit more directly, I'm sure. I just found a shortcut and did it, so that's what I went with. Okay, so then it has pH twice. This is just kind of ease of graphing. We'll just do equals that guy. We've got log of H plus. So if we take the log of our H plus, that's just going to be essentially negative pH. And of course, 0 is 0. And we could do log of our OH minus, fill that down. So a lot of this stuff you can probably do relatively quickly up until you get to these fractions, or these portions. And there's some question maybe about what the denominator needs to be. If we're taking a look at our systems like this, depending on what we're solving for, you know, actually, as I'm taking a look here, it's kind of interesting. I just noticed that the denominator is the same in all of these, and I think that's maybe part of their analysis. So what they did was that if you derive this in the manner they did, the denominator is the same for each of them. So all the fractions are the same, and then the numerator is different. So I think that's where they were going with this. And so for the denominator, that would be H plus squared plus K. So let's go ahead and do it. So for the denominator, it should be H plus squared plus K1 times H plus. So I'm just going to do H plus times K1, which is back here somewhere. Ka1 is right there. And then we need plus the K1 times K2. So K1 times K2. And this is where it might be the case that the sulfuric acid just blows up in my face and doesn't work at all because it's such a silly K value. But we'll see. So that gives a denominator value there, and we can fill that down for each of the pHs that we're going to have. Then let's see. Probably should actually take a look at the prompt at this point. I think that's what it's referring to for the denominator. And you know what? I made a big mistake there. I didn't freeze the panes. So when I called the H plus, that was fine to fill that down. But when I called the K1 and K2 and then filled those down, then it's now K7, K8, or excuse me, cell B7, B8, B.
Yeah, and that's what I was on the email view, and I was going to tell you, like, it works really good if you make K1, K2, PK1, and PK2 just a label at the top, and then just fill them in as the same value all the way down, or you can freeze them.
Yeah,
I didn't know about that, so I just filled them all the way down.
No, I need to. So the Excel the worksheet tells you, hey, define the names like this, and I've never done that, so I need to actually go and do that. I probably should have done that first, so I could show you guys how to do it. But that's something that I was looking at. I was like, I haven't done this. It's an old version of Excel they're working from, but it works. You know, this process is still there, so we can define a cell. If you follow the instructions, it's going to be very close to it, and if you need, just define name here. So we can call one specific cell K1. I think it is kind of how we can work at, or something like that. I'll take a look, and if you guys are interested, we'll be able to answer that later. It's obviously not relevant for the exam, and there's multiple ways to do this, as is usual. So I'm glad to hear that you were finding it useful there. I'm just going to freeze them real quick because I don't know what I'm doing otherwise. So we'll just go with that, fill those down again, and get different numbers this time. Yeah.
If you highlight KA1 and KA2 with their numbers, you can go to the formulas part and do create from selection, and it will automatically name KA1 and KA2.
Cool. Okay, so the formula in here?
Yeah. See the create from selection? It's like in the middle, at the bottom.
Gotcha.
If you highlight like A5 through B6 and do create from selection, it'll name them.
Like that?
Yeah. And then do that, and then do left column. That's the one it's named it from.
Cool. Okay, so then it just defined KA1 as this guy and KA2 as this guy, essentially. And then I can call that when in here, instead of writing out the cell, I can do KA1, essentially. Cool. So let's do that. So here we had KA1, and yeah, I see it's filling that here for me. Was it KA1 times, I already did that. Okay, so plus KA1 times KA2. Cool. So presumably then that will, did I do something different? Oh, my naming is bad. That's calling the cells KA1. So if we scroll really far to the right, then I just accidentally called some cells that are way over there, right? Because the cells start repeating. Okay, you could go all the way out over to here and up a few and find KA1, right? That's what I accidentally just called. Okay, so I think that should work if I had just either thought of a better name or probably typed it in wrong here. So let's see if I can get that. I mean, it looks like I can, if I click that, any ideas for me here?
I think it does work if you click it. Or if you just click the actual value.
Oh, there we go. It has a subscript after it. Interesting. And I had to double click it with my touchpad. So KA1. Yeah, I think if you just add that underscore afterwards, that fixed it. KA2. Yeah. Okay, there we go. Yeah, and I had already fixed that, so that should be good. Cool. Thanks. All right. Okay, so at that point, I would actually need to go back and read the assignment. Pretty sure that's kind of a good start to it. part of this is going to be plotting. And I assume there's several different things you can do for that. And again, remember, I'm gonna, whoever makes the most attractive plots, figures, data visualization, I will give some extra points to that. So do your best there. Let's see. So at this point, they want formula for each of these based on the H plus concentration. So essentially what we're looking for is so this is a fraction. What we're more looking for is, let's say, the HSO4 minus in terms of H plus concentration. And I think we should just be able to simplify in just the form of H plus and the Ks for that. So that's going to take some simplification. Now, this denominator term, maybe what's going on is what we're actually talking about is just get this guy, and this guy in those fields, and then we're going to divide that. If we're looking at the fraction of the total, I think maybe that's what they're doing. So I'm going to bet that those three are what's going on for these three fields here, because then we have the numerator there, and then the denominator for each given pH that we can divide by. So I think that's what's going on. I need to take a closer read, but I'm going to move on in that direction, assuming that's kind of what they're looking for. So for the H2A here, so this is simply going to be equal to the pH squared. We can fill that one down like so. For the HA, this is going to be Ka1 equals Ka1 times H plus concentration. Fill that down. And then finally our A here, this is just K1 times K2. And that should be the same throughout the whole bunch. Okay, so I think those are the portions, and then we could take the log of those. Maybe we need to include the denominator there. Maybe it's, because one thing we could do is just divide that by the denominator portion that we already calculated.
I think that's what I did in mine.
Yeah, that makes more sense because we're actually at least putting it in brackets and saying that's the concentration. That would make more sense. So I think that's probably the better way to do it. So we'll go ahead and divide each of these. Makes more sense. Okay, so then we can take the log of each of those. Oops. And those will be quite easy to fill. You can fill that down and to the right. So Control D and Control R. That should get all those correct. Yep. Okay, so maybe that's most of the assignment right there, if we did that correctly. Okay, so then there would be a matter of graphing, of course. And again, I think this case may not be let's take a look at the concentrations. Okay, a lot of HA, so a lot of HSO4 minus at low pHs. That seems like it makes sense. And practically none of the H2SO4. Well, there's a little bit at pH 0, a little bit at pH 1, and by the time we're down to pH 5, there's very, very small amounts. So that actually kind of makes sense. And like I said earlier, the SO4 2 minus, the reason sulfuric acid is such a strong acid, it just wants to get rid of those protons. Just wants to be sulfate and protons. Right? It just wants to get rid of them. And so by the time we're down near a neutral pH, we are really pretty much all sulfate, dissociated all the way to sulfate. So then we could graph different plots. I don't know what actually it's asking us to graph, but let's take a quick look just to see what it looks like if we are to, let's give scatter with curves. Let's take pH and these log values. And if I just select it like this, maybe that'll be, actually, hang on. Try that. Let's see if this looks good. Okay, so I think it kind of worked. I don't love it, so I want to edit, instead of using log of H, I think I do want pH. It's probably the wrong way to do it. Anyway, okay. So at any rate, I think this is hopefully pretty useful. Lots of different plotting things you can do, and if you'd like, I'm happy to keep staring at my screen and working on that for you, but otherwise I think I'd rather we just take a quick Kahoot and let you get on your way. So any questions? Any thoughts, comments? You guys tried the homework? Is this helpful here? Hopefully. Well, now you've got a heads up on it. Yes, I can. All right, anybody else need a moment? Is this the best part of class? Next time I should do a Jeopardy music and make it a difficult problem. All right, see you guys on Thursday.
Agreed.